Alright, so after a quick costume change, let's see. We left off talking about how to calculate the total magnification of a microscope. We were discussing that the total magnification is the magnification of the first lens multiplied by the magnification of the next lens and the next lens and so on and so forth. So in a microscope, you'll have two lenses, a light microscope specifically. These two lenses are going to be your eyepiece and your objective. The eyepiece is always going to be a 10 times magnification. So anything you look through with just the eyepiece is going to be a 10 times magnification, which means objects will appear to be 10 times larger image size than the actual size. The objective can vary depending on whether you are on low, medium, or high power. Low power objective will be 4 times magnification, medium will be 10 times, and high power will be 40 times. Your total magnification will be 4 times 10, 40 for low power, 10 times 10, 100 for medium power, and 40 times 10, 400 for high power magnification. Now, these are some those were some links to videos of things that I'm a fan of. Not sponsors, I'm just a fan. So here are differences between the two different types of microscopes that we are going to discuss for the most part as part of AS level curriculum. Light microscopes and electron microscopes. The light microscope, the design will vary, but effectively you're going to have an eyepiece, your ocular lens, usually will be 10 times magnification. You'll have a revolving nose piece. In the microscopes that we use, we have a revolving nose piece. You don't always have to have this. The microscopes that we use have 3 different objectives, a low, medium, and high power that I've already discussed, their sizes. We have stage clips which hold the microscope slide in place. We also have mechanical stages on our microscope which allow you to move the stage in an X and Y axis plane without having to touch the microscope slide with your bare hands. We also have an iris diaphragm, which we can open and close to allow more or less light in through an aperture. We also have a projection lens, which allows light to come up through a light bulb. A heavy base, there's power switch because we have an electric light bulb. There is a power cord. And of course, if you can't see anything, the first thing you should do is check to make sure your light switch is turned on. Now, there are a coarse focus and a fine focus knob. Ours are separated on our model microscope. But the coarse focus may only be touched when you're on low power magnification. Touching the coarse focus when you're on your medium or high power magnification can take the stage and raise it up into the lens, crushing the lens. You can actually damage the microscope in this way, and you'll have to buy a new one. So the fine focus is the focus that you use to sharpen the image when you've actually brought it into focus and you can see anything. Now, electron microscopes are extraordinarily expensive. In fact, the difference between light microscopes and electron microscopes that you can cite on an exam is that electron microscopes are more expensive than light microscopes, and that's why you should use a light microscope when you're doing such and such experiments. Because light microscopes are cheaper, and they require less expertise to use. Those are good reasons to choose a light microscope over an electron microscope. Electron microscopes require specialized training. They are very expensive. They require a lot of power, a lot of electricity. So, this is a transmission electron microscope design, most likely, but because a transmission electron microscope uses electrons in order to view a specimen instead of light, you need to control and focus that beam of electrons instead of light. Now, light you can focus using a lens, but you can't really use a glass lens on electrons. That will just block the flow of electrons altogether. Instead, with an electron microscope, you focus the electron beam using a lens that is an electromagnet. Because electrons respond to electromagnetic waves and magnetism, because they are the same force, thank you physics, you have a series of magnets. You have a series of magnets in an electron microscope that focus and refocus the beam of electrons. Your specimen is in a vacuum chamber inside of an electron microscope, and it is prepared in a very special way that usually results in the death of the specimen, if it was ever alive to begin with. So, whereas in light microscopes, your specimen can be alive and moving and swimming, in an electron microscope, your specimen will die. If not during the preparation process, then certainly when you fire a beam of electrons through it and electrocute it to death. So, and possibly also push it through a vacuum chamber and evaporate all of the water inside of it. So, electron microscopes are not conducive to water-bound, water-filled specimens, or even specimens contained in water. Now, the electron beam will go through the specimen in a transmission electron microscope. In a scanning electron microscope, the electron beam will bounce off of the surface of the specimen and then go through a series of aperture lenses and intermediate lenses, etc. And then that electron beam will be diffracted onto a fluorescent screen. That fluorescent screen will detect whether or not there was or was not an electron scattered. And if there was, it will be a yes. And if there was not, it will be a no. It's a binary, yes, no. So that will be a white pixel or a black pixel. That is, in effect, why all electron microscope images are black and white. They are all monochromatic. They are black and white. Light microscope images can be in full color, but electron microscope images are all black and white. Now, you can add color to an electron microscope image. Those are called false color images. And for that, an artist actually has to come in and be paid, because you should pay artists for their work. This is YouTube, after all. And they will color that image after the fact. Now, you view the image after the fact because your eyeballs cannot ascertain electrons. You have to project the fluorescent screen onto a computer screen that you can see. So you have to compute this image. Now that, in a nutshell, is the functioning of an electron microscope. This is an expensive process. This is a long process. This grants you still images. You cannot see movement with this. You cannot see living specimens with this. But because electrons are much smaller than light waves, you can see much smaller objects. You can see much greater resolutions. Overall, this gives you a greater quality of image. It also gives you greater depth of field. The size of the specimen that you can see will be greater in a light microscope, but depends on your price range in the electron microscope, what all information you want to get out of it. Now, a light microscope uses visible light that passes through an object and is focused on the eye by means of a series of lenses. An electron microscope uses beams of electrons passed through an object or focused on a detector plate using electromagnetic fields. Scanning electron microscope, SEM, they are used for surfaces of your specimens, whereas transmission electron microscope is used to visualize internal structures. Light microscope can view things in their natural colors. Electron microscopes only give you monochrome images. Light microscopes give you a large field of view. Electron microscopes will limit that field of view. Light microscopes are cheap and easy in your preparation. Electron microscopes are very difficult to prepare, and they are extraordinarily expensive. You can view living and moving objects with light microscopes, and electron microscopes, you can only view dead and inert objects. Light microscopes, your magnification will be lower, and your resolution will be lower. Electron microscopes, your magnification will be greater, and your resolution will be greater. There is no trade-off here. You don't get better resolution and better magnification. There's no better magnification for worse resolution. There is only better. In terms of magnification resolution, electron microscopes, straight up better. But these are all the reasons why electron microscopes are inferior to light microscopes. But this is a big plus. You can see a lot smaller stuff with a lot better image, with quality that is greater. So this is a light microscope of a transverse section through a vascular bundle, most likely, of some plant specimen. This would be a similar scanning electron microscope image of that same plant specimen. Now, black and white, once again, all the dark spaces here are going to be air and nothing's going to be present inside those. But you can see that there is a similar scale. You get better resolution. You actually see more detail in the actual walls of the cell walls of the plant cells. So you get better resolution for the same scale, for the same magnification. This is a transmission electron microscope of just these pink sclerenchymal cells right here. So these transmission electron microscopes visualize the internal structures of the cells themselves, these very thick cell walls. Now, resolution. The size of the interval between two separate points in an image is the resolving power. That's the resolution. Resolving power, is the capacity of an instrument to resolve 2 points which are close together. When an object is resolved, you can distinguish those 2 points. When an object is not resolved, you can't. This means that a smaller interval between these 2 points being resolved means you have a higher resolving power, higher resolution. Higher resolution gives you less grainy images when you zoom out. So here is an image, and here is a zoomed out image that is super grainy because you have small interval between, you have a large interval between pixels. We don't ever care about individual dots. We care about resolution as it pertains to our ability to see specimens. So this is a light microscope image with the same scale as a electron microscope, scanning electron microscope image. This is a radiolarian. It's a sort of protozoan fossil kind of a thing. It's a single-celled, it's a protozoa. It has a mineral skeleton. So it produces these really cool, intricate shells that are super tiny. If we want to magnify, we only want to magnify things up to the level that we can resolve. Otherwise, we're not going to be able to see stuff. Now, for light microscopes, that limit of resolution ends up being about 1,000 times magnification. And the reason for that is a physical reason. The physics is that 200 nanometers is slightly less than half of the visible wavelengths of light. Red light is the smallest wavelength of light that we can see. Half that wavelength, less than half of that wavelength, and light waves cannot bounce off of objects. Visible light waves cannot bounce off of objects. So light microscopes that use visible light cannot resolve anything smaller than 200 nanometers because the visible light wave is too large to actually hit such a small target. It's like firing a cannonball at a mosquito. Wow, that came out wrong. It's like firing a cannonball at a mosquito. I am glad this is such a professional operation. Alright, so it's like firing a cannonball at a mosquito. Too large, you're not going to hit it. Alright? So the wavelength that you're using of light is just too large. It will pass right by that object that you're going to see. You will never hit that thing. It will not bounce back. You will not detect that wavelength. You will see nothing. So smaller than 200 nanometers in diameter, you will see nothing. That is the limit of resolution of light microscopes. On the Cambridge exam, this is a good excuse for why you can't see certain things. You cannot see certain organelles because they are smaller than this size. You cannot see membranes because membranes are smaller than this diameter. You cannot see chromosomes that are not condensed into, because the diameter of a chromosome is 2 nanometers, because DNA strands are 2 nanometers in diameter, as we discussed previously in Unit 1. But a condensed chromosome can be 30 nanometers for chromatin and beyond, 200, 400, etc., for that width of that chromosome, which we'll discuss more in Unit 3. So as these chromosomes condense, we can see them, but we can't see them when they are too small. Now, transmission electron microscopes versus scanning electron microscopes. Transmission electron microscopes are actually better at resolving smaller things. Their magnification, their power of magnification is more intense. They were developed first, though. In here, the beam of electrons passes through the specimen and then is scattered onto a detector. Versus the scanning electron, where you bounce the electrons off of the surface of the specimen and then onto a detector, and that shows you surface features. They each have their place in scientific inquiry, but I personally think that scanning electron microscopes look prettier. Their images are just cooler. But transmission electron microscopes are definitely more useful in a lot more circumstances. You're going to see smaller stuff, and you're going to be tested on them more often. Just from an academic perspective, transmission electron microscopes are more useful. Now, this is a light microscope comparison. These are plants, these are animals. You can recognize light microscope images because they are in full color. They are not terribly well resolved. You're not seeing great depth perception. You're seeing that you're not seeing many individual organelles. You're seeing large structures pretty much exclusively, not individual small organelles of any sort. And here's a transmission electron microscope. These are the extent that you can see. You can see everything down to the 2 nanometers and below, down to nearly below in the picometer range. You can't see individual atoms yet, but we're close. So we can see individual layers of graphene. These are single layers of carbon atoms that you can see here. You can't resolve the individual atom, but you can see the layers. Now, mitochondria, you can see the individual folds that are called cristae here, and the double membrane that exists. Here we see a unicellular organism. This is a prokaryotic bacteria with a capsule, or a cell wall, excuse me. And this is the cellular membrane. You can see a cell membrane, which is around 7 to 9 nanometers in diameter. In width, excuse me, width, not diameter. This scale bar right here shows 0.25 micrometers in this distance. And this is a transmission electron microscope, a broken snowflake, as it were. This is 1 millimeter. So snowflakes you can actually see with your naked eye. You can see them falling if you didn't live in Florida. By the way, we're filming in Florida. Hi, people in the north who are cold right now. This is a scanning electron microscope image. I thought you said water evaporated. Well, you have to cover it in platinum first. So this is a snowflake that was then encased in metal, and then you scanned it. During the preparation process, that spike probably broke off, and a lot of the details were lost when it got covered. So, and this is a tardigrade, my spirit animal. And this is also a tardigrade. This is a false color image, as promised. So a false color image, where you have your algae in the background that's colored green, your tardigrade is colored tan, and then you have a light microscope image of a tardigrade. I like tardigrades. The internet loves tardigrades. So here we have our digestive system right here. We have the individual cells of the tardigrade throughout here. We have our claw feet, 1, 2, 3, 4 feet. We have our sucker right over here. We have our little eye stalks. Well, not really eye stalks. They're really more of like receptor pods, whatever. And, of course, some memes about the tardigrade. Yes, they'll live through anything. Well, they'll die through anything, but they'll come back. They'll be back for you. All right? Now, tardigrades, more links. They are cool. If you don't agree, I don't agree with you. Now then, let's talk about individual cells. Plants versus animals. There are some differences here. I'm going to point out these are eukaryotes. I'm not talking about prokaryotes yet. We have here a cell membrane. We have a cell membrane here in yellow. We have a lysosome. We have a lysosome. We have ribosomes here. We have ribosomes here. We have peroxisome. We have peroxisome. We have Golgi. We have